Hello and welcome to the lesson on the constant acceleration formulae. There are 4 constant acceleration formulae in physics which you use all the time. And they explain how an object moves, how it increases its velocity, the distance it covers, the time it takes, all under a constant acceleration. And these formulae are very useful because they reveal things about an object's motion that you might not figure out unless you were able to use some calculus. It's basically calculus made easy for you in these formulae. So first of all, we'll define our terms. We have S. The variable S is displacement, which is basically the distance and direction of an object from an origin. Then we have U, which is the initial velocity. It's the velocity, basically t equals 0. We have V, which is the final velocity. It's the velocity the object reaches. We have A, which is the acceleration. A never changes. And we have T, which is time. And we'll set up some units for these. Displacement is usually in meters. Initial velocity is in meters per second, final velocity meters per second, acceleration meters per second squared, and time in seconds. So let's look at the first formula. That would be V, oops, can't see that, V equals U plus AT. So first of all, I'll remind you, A is equal to delta V on delta T, the change in velocity over time, or the gradient on our velocity versus time graph. So on this graph over here, we've got velocity versus time. Don't mistake this V for the final velocity. This velocity is the velocity at any point in time. Say we start out at U. That's our velocity at the start. So the height of this line here is U. And then we end up here at V. Gosh, all I want is a straight line. There we go. And the height of this line here is V. This formula here explains the connection between these, because linking these two lines, linking these two velocities, is this line here of gradient A. So the gradient of velocity of a velocity time graph is the acceleration. So linking any two velocities, if we can draw a line, the gradient of that line is going to be the acceleration. So if we start at U, we're starting at this height here. So I'll draw a horizontal line. This would be U on the final velocity. And the extra rise here, we'll call that the change in V. And of course, this length along here is delta T. The formula here basically says, if we start out at height U, which is here, and then we add on delta V, which is here, we will get to the final velocity. And the reason that delta V is given by AT is because we said A is equal to delta V on delta T, and if we multiply that by T, or delta T in this case, that's when we get the delta V. Another way of looking at this formula is we can rearrange it. V take U equals AT, V take U on T equals A, V take U is the change in velocity, so that's change in velocity, and T in this case is the change in time. So it simply tells us that delta V on delta T is equal to A. So that's how the first formula came about. Yes, I can keep my axes. Let's have a look at the second formula, which is a bit more interesting. S, the displacement, is equal to half U plus V times T. So let's look at this again. We say we have this first velocity U, the final velocity v, and we have the velocity, since it's a constant acceleration, has to be a constant gradient between these 2 points. We're trying to figure out s. Now we said in lesson 1, the area under this graph here is equal to s. So that'll give us a clue as to why this particular formula works. This shape, it's a four-sided shape known as the trapezium. And the area of a trapezium we learn in school is you take the top A, the bottom B, and you find the average, which is A plus B on 2, and you multiply that by the height. This graph here is basically a trapezium tripped on its side. Oops, I'm selecting the wrong thing here. So we have V over here, which is A, and this height here, which is B, and then the height would be T. So the area of this entire shape here is equal to a half V plus U times T. Finding this formula enables us to find the area under a velocity time graph and therefore the displacement. Finally, second last, we have S equals UT plus half AT squared. Let's draw this graph again. There's the starting velocity U. Here's the final velocity V. Here's the line of constant acceleration. And we want to find the area under this graph. First of all, we break it off into two halves. Here we go. Two regions. The area of this region plus the area of this region is going to be the area of the entire shape. Now the area of the bottom is easy. This side length here is U, this side length here is U, this side length here is T. So this area here is UT, and that area corresponds to this part of the equation. Now the area up top is a little more difficult to find, but it is a triangle. So before we said the gradient of this line is A, and the height of this section here therefore has to be AT, and the length of this section here is equal to T. Now this is a triangle, so the area of this section in here is equal to a half base times height divided, a half base times height. So the area, say A1, was equal to UT, and A2 was equal to a half base, which is AT, times the height, which is T. I'm saying this is the base and this is the height, excuse me, I should have done the opposite way, which is a half AT squared. And the total area is equal to A1 plus A2, which is UT, plus a half AT squared, which is the formula we have. So again, this is just a way of finding the area under a velocity time graph. Now the final formula, it doesn't so much deal with the area under a graph, but it is a type of energy formula, and it looks like this: V squared equals U squared plus 2AS. This formula is very useful when you're given the distance something moves, the acceleration it moves at, and say the initial velocity, and you can use that to work out the final velocity. And although I can't represent this graphically, later when we do energy we'll see why this particular formula works. So that's the graphical explanation to all the formulae. It's good to have, but the most important thing to remember is if we give all the formulae, V equals U plus AT, S equals a half u plus v times t. S equals ut plus a half at squared, and v squared equals u squared plus 2as. Say you had a bit of information. A car, initial velocity equals 10, accelerating at 1 meter per second, and the time is 5 seconds of acceleration. If you have these three variables, let's look at what you could find. You have a, u, and t. Hey, this formula up here has a, u, and t, so we could find v. Furthermore, this formula down here has a, u, and t. So if we plug these values in here, we could also find s. So from only three variables, we could find the other two. Depending on what information you're given. If you're given, say, the velocity, the final velocity, the initial velocity, and the distance an object moves, you can use this formula down here to find the acceleration. And you can also use this formula here to identify the time. So you've been given four formulas here, so that no matter which three variables you're given, you can work out the other two. So let's do a problem below and we'll show how all these formulas fit together. Say there's a car, it's just coming back from Falls Festival, and it sees a police car on its tail and it decides to run from that police car. It decides to try and evade the police. It has initial velocity of 10 meters a second. It has a final velocity of 20 meters a second, and the time it took to go from one velocity to another is 5 seconds. So we have u, v, and t. Let's see which formulas we could use. Hey, this one up here works. V equals u plus at. We want to get a by itself. Actually, we'll solve it the easy way first. 20 is equal to 10 plus a times 5. Take 10 from both sides. 10 equals 5a. Divide both sides by 5. 2 equals a. So we found a equal 2 meters a second. Now here's a better way of solving that. We knew we had v, t, and u. We lay out our formula. V equals u plus at. This is the one we want to find, so we try and get this one by itself. V take u equals at. V take u on t is equal to a. Now we sub in all our information down into here. That would be 20 take 10 on 5 equals 10 on 5 equals 2. So we found a. We might also want to find s. So let's look at which formula we can use. We know we have t from the start, u and v. We also found a, but hey, let's not trust our answer. Let's just go with what we've been given. S equals a half u plus v times t. We'll use that formula. S equals 1/2. U was equal to 10. V was equal to 20. T was equal to 5. S is equal to a half. 30 times 5. That's equal to 15 times 5. 75. So it went 75 meters in the time between these two velocities. Whilst it was accelerating, it was covering distance. So, as you can see, even if we start with just three simple variables, or only three knowns, we can find the other two knowns. Let's test this final formula to see if it really is true. It says v squared equals u squared plus 2as. I'll move everything over. So say we had v squared. V squared is equal to 20 squared. U squared is equal to 10 squared. 2as is 2. A was 2. S was 75. This tells us that 400 is equal to 100 plus 4 times 75, 400 equals 100 plus, well 4 times 75 is 2 times 150 equals 100 plus 300 equals 400. And so that is a true formula. Well, we think it's true. It's not quite confirmed with just one example, but you can try them out. So the number one thing to remember is that if you're given 3 variables, you can run them through all these formulae and you'll settle on the other 2 variables as knowns if you apply these formulae. There'll be a few example questions done in other videos. If you want to see how these formulae are applied to different questions, check those out.